Okay, now let's look at the situation where we start out with two substituents already on the benzene ring. So this is a little busy here, but this is what we've got. We've got a para-nitrotoluene, CH3, nitro group para-nitrotoluene. And we're going to put Br2FeBr3. Well, we know Br2FeBr3 is going to put a bromine somewhere on this ring. The question is, where is it going to go? Well, this group and this group are going to duke it out. With this example, we don't have to worry about it, because recall that alkyl groups, like methyl, are ortho-para directors. There's already a nitro group para, so it cannot put a bromine para. Nitro's taking that spot. Recall, all these reactions, Friedel-Crafts, all these reactions take a hydrogen off. They cannot take a different substituent other than hydrogen off. So the para position already has a nitro, which means the CH3 is going to put group ortho. Recall a nitro group, strong deactivator, and directs things meta, directs the next substituent meta. So note, meta to this nitro group is here and here, the same as ortho to the CH3. So this is pretty straightforward. We're going to put one bromine on there. And note, nitro group is a deactivator, so we will not get two bromines. We'll only get the one bromine on here because this ring is deactivated. All right. What about this situation here where we have our acid analyde here, our amide group, and a CH3? Well, this methyl group is an ortho-para director. Well, para is already taken, so the methyl group wants to put our bromine here and here, ortho to it. But note, acid analyde is also an ortho-para director. It wants to put the bromine here and here. So methyl wants to put the bromine here. Acid analyde wants to put the bromine here. Which is going to win? Well, which is the stronger activator? Recall from our table, there's our table, acid analyde, this group, our amide group, is a stronger activator than alkyl groups, which tells us that it's going to go, the bromine's going to go ortho to the nitrogen, to the acid analyde, because it is a stronger activating group, therefore a stronger director than the methyl group is. Cool. All right. Let's look at this one here. What if we have just camera? What if we have the situation where we have a benzene ring with two methyls? Does anyone remember the name of this? Yeah, there's lots of names for it. You could call it metamethyltoluene, but does anyone know what we call this? Two methyl groups meta to each other on a benzene ring? Recall, this is metaxylene. Yes, we have metaxylene here, and we want to react Br2FeBr3. We need to put a bromine. Note, this methyl group wants to put it ortho or para. This methyl group wants to put it ortho or para. Turns out, though, that in between the two methyl groups, it's just too crowded. Steric hindrance means that even though these are both ortho directors and want to put ortho to themselves, they won't be able to do that due to steric hindrance. So the bromine will either go ortho to this methyl, which is meta to this one, or here possibly. Well, no, it wouldn't go here. Tell me, why wouldn't the bromine go here? That's right, because this position is meta to both these two methyl groups, and methyl groups are not meta directors. They are ortho-para directors. So the only place it could go is here or here. And if you realize, I drew the molecule with the bromine going here. If you were to draw the molecule with the bromine going here, you'd find out those two are actually the exact same product. They are the exact same molecule. You just flip it around and you get the same thing. So you only get this one product here. All right. And here's another situation For example, we have a methyl on with a nitro ortho to that methyl group. And what if we put HNO3, H2SO4? First question, what does HNO3 and H2SO4 put on a benzene ring? It puts a nitro group on the benzene ring. Note, nitro is a very strong deactivator, but it's also a meta-director. It's a very strong meta-director, so truthfully, the methyl doesn't have much to say in it. But either one, whether it's the very strong nitro deactivating meta-director, it wants to put the next nitro group meta here, and the methyl group here is an ortho-para director, ortho and para to it, so ortho to it's here, meta or para is here. So either way, the next nitro group goes down here or here. Okay. But note, this is a very deactivated ring. It's a very deactivated ring. Note, what if you tried to do it again? What if you tried to put a whole nother nitro group on here? Where would the next nitro group go? Well, think about it. Pause the recording. Okay, the next nitro group would go right here. So you would end up, if you put a third nitro group on here, you would end up with our benzene ring CH3, NO2, NO2, NO2. This molecule, by the way, is based off of toluene. CH3, a benzene ring, is toluene, so it's a toluene, and it's got the 3 nitro groups. So if this is carbon 1, this would be carbon 2, 3, 4, 5, 6. So this is 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene, also known as TNT. It's a fairly unstable molecule. It is an explosive. However, something to realize, this is trinitrotoluene. It's not dynamite. Yeah, there's an old AC/DC song, TNT, it's dynamite. No, trinitrotoluene is not dynamite. Dynamite is actually a special nitroglycerin type molecule on a support. This is a different molecule. This is TNT. It is not what makes dynamite. So sometimes even our best rock bands lead us astray. Not that I really care for AC/DC. Sorry, not one of my favorites. All right, so let's look at some synthesis now. Starting with benzene. Well, it's too late. It's already on the video. But starting with benzene, how would you make this molecule right here if you had to start with benzene? Well, we know 2 reactions. We know how to put a chlorine on, Cl2 FeCl3. We know how to put the sulfonyl group on, SO3 and H2SO4. The question is, which one do we put on first? Well, note, these 2 are meta to each other, right? So if we put the chlorine on first, where is chlorine going to direct the sulfonyl group when we put it on? Well, recall, chlorine, while it's deactivating, is an ortho-para director. So if we put the chlorine on first, the sulfonyl would go ortho to the chlorine or para to the chlorine, but it's not, it's meta. So what would happen if we put the sulfonyl group on first? Well, if we put the sulfonyl on first, we know that that is an meta director. Sulfonyl is a meta director, which means we put the sulfonyl on first, and then we put the chlorine, because the sulfonyl will direct the chlorine to be meta. So if the question is, starting with benzene, how do you make this molecule here? The answer is, you start with benzene, SO3H2SO4 to put the sulfonyl group on, which is a meta director, then Cl2 FeCl3 to put the chloro group meta to the sulfonyl. All right. Cool. On the exam, there will be several questions along this. How do you make this molecule? How do you make that other molecule? You have to know the sequence, or figure out the sequence. All right, halogenation of alkyl benzenes. Turns out the benzylic CH bonds. So if you've got a benzene ring and a carbon next to the benzene ring, a carbon bonded to the benzene ring, this is the benzylic position. The carbon bonded to the benzene ring is a benzyl carbon. Note, not the carbon of the benzene ring, the one next door. This is the benzylic carbon. It turns out this carbon-hydrogen bond is fairly weak and is likely to undergo homolytic cleavage and delocalization to make a radical. So what's going to happen is the carbon-hydrogen bond will break homolytically. One electron will go to this hydrogen, one electron to go to the carbon, make the carbon radical. Turns out benzene rings can delocalize that carbon radical, which makes it kind of stable. Which means, that's a long way of saying that if the product is a little bit more stable than you think it would be, then this reaction is more likely to go. Therefore, the carbon-hydrogen bond is more weak than you think it would be for homolytic bond cleavage. Which means, check this out. If you had ethyl benzene and you just said Br2 FeBr3, this is our normal, okay, this is an ethyl group, it's an ortho para-director, you would get this. But what if we put it under radical conditions? What if instead of Br2 FeBr3, we did Br2 heat or light, radical conditions? Well, if we put bromine in with the ethyl benzene under radical conditions, we know, due to what we said here, we're going to make a carbon radical right here, and that's where the bromine is going to go. So you can put a bromine right next to the benzene ring, on the carbon next to the benzene ring. Note, though, you can't put the bromine out here at the methyl group, and if you had a butyl group on here, it doesn't matter. The bromine will go at the benzylic position because it's the benzylic carbon that likes to form the radical. All right. So let's do a little bit more synthesis, shall we? Here we have a benzene ring with an OH on it. How would you make that benzene ring starting from, or with OH on it? How would you make this molecule just starting from benzene? Note this is a little bit more in depth. Takes a little bit more thinking now. Well, first say, okay, I know this is a 2-carbon system, so I need to put an ethyl group on there. How do we put an ethyl group? Well, let's try Friedel-Crafts. And maybe if we're good, we can do this Friedel-Crafts alkylation and only put one ethyl group on there. Now we know we need to do something with this OH here, right? But we need to somehow put an OH on there, and I'm not sure how to put an OH on there, but I know how to put a bromine on there. And once I've got a bromine on there, how can we change a bromine to an OH? Well, here's how we're going to do it. We need to put a bromine on here. Well, that's pretty easy to do. Br2 heat and light. Radical conditions of Br2 puts a bromine on the benzylic position. And note, this is a secondary alkyl halide. We can just do an easy SN2 reaction with hydroxide to get that. Now recall from the SN1, SN2, E1, E2 chapter, we've got a secondary alkyl halide which can do SN1, SN2, E1, and E2. We've got hydroxide, which is a strong base. Therefore, that tells us we'll either do SN2 or E2. So truthfully here, you'll probably end up with a mix of SN2 and E2 products if you did it that way. But I would accept that on an exam because one of the products is this. And if you recall that adding heat favors elimination. So if you ran this a little cold, kept the temperature down, we can probably maximize our SN2 product, put the OH there. Another way to do it, though, is once you put the bromine on here, is just don't worry about the substitution. Do the elimination. Do potassium tert butoxide and make a double bond here. Just do the elimination, the dehydrohalogenation of the H on the methyl and the Br here to put a double bond there, good old beta hydrogen elimination, and then just acid catalyzed hydration of an alkene to make an alcohol. Recall Markovnikov's rule. The hydrogen will go on the carbon with more hydrogens. So the hydrogen will go here, which means the hydroxide, the OH group, will go here, and we will get that. So, yeah, if you're running this, probably the better way to run it would be to do it this method. Do the E2 elimination, because that reaction will go 100% this way, and then do the acid catalyzed hydration, because you'll go 100% to this molecule, instead of having a mix of your product you want and the E2 product. It just means you'll have to do a separation, fish out the E2 product, and then do the acid catalyst right there. So this would be the better route. However, if you on an exam did this or this, both would get 100, all the credit, because you did make the correct molecule. All right. Cool. Let's see. Well, we've got that to worry about. All right. Redox. If you have at least one benzylic carbon-hydrogen bond, potassium permanganate will convert a benzene ring with at least one carbon-hydrogen bond at the benzylic position into benzoic acid. So if you have a methyl group, or an isopropyl, or two ethyls, potassium permanganate changes it to carboxylic acid. What about all this other stuff? What about these two CH3s? They're gone. This carbon here, the benzylic carbon, whether it's a methyl, isopropyl, ethyl, that carbon gets converted to the carbonyl of a carboxylic acid. Note, though, you have to have a carbon-hydrogen bond. So if you had a tert-butyl group here, this carbon of the tert-butyl group, the benzylic carbon, does not have a hydrogen, so potassium permanganate, no reaction. We've already covered this. If you have a benzene ring with a carbonyl attached to it, you can do a Clemmensen reduction or a Wolff-Kishner reduction to reduce that carbon. Note, not to the alcohol. Recall chapter 12, we could reduce carbonyls to alcohols. Now we can reduce carbonyls to CH2s via Clemmensen or Wolff-Kishner. Here's an interesting one here. If you have a nitro group, you can use H2 palladium on carbon, our standard catalytic hydrogenation, and reduce that NO2 to an NH2. So this is how, no, we haven't found a way to add NH2 to a benzene ring. You can't just take a benzene ring and add NH2 to it, but you can make nitrobenzene, take a benzene ring, put a nitro group on it, then reduce that nitro group with H2 palladium on carbon, catalytic hydrogenation, to the NH2, to the amine. All right, and note, H2 palladium on carbon will work because you have a lot of palladium on carbon around. If you do hydrogenation, FeHCl, H2 tin, and HCl will also work, all three of these methods. If you see a nitro group, H2, and some sort of metal, you're reducing that nitro group to aniline, or that nitrobenzene to aniline. Note, though, if you have a nitrobenzene and a carbonyl in your molecule, H2 palladium on carbon will reduce the nitrobenzene. As long as you add one equivalent of H2, monitor the amount of H2 gas you're putting in there, you will reduce the nitro group to aniline, to NH2, to the amine, and you will leave the carbonyl alone. This molecule, by the way, is benzocaine. This is one way to make benzocaine. In the lab, we're going to find another way to make benzocaine, also known as Oragel. Good for itches and sore teeth and things along that line. All right. So, the last page, I'm just going to end this by showing you this last page. This is synthesis. This is stuff you need to work out. So, starting with benzene, make this molecule. Make this make metabromoaniline from benzene. How do you do that? I'd recommend you stop the video and work on it. Okay, now I'm going to show you how to do it. Note, we've covered it before. NH2 is an ortho-para-director. Bromine is an ortho-para-director. So it doesn't matter if you put the NH2 on first or the bromine first. Both of them are ortho-para-directors. So how are you going to work this? But then you said, wait a minute, I cannot put an NH2 on here. How do you get NH2 on a benzene ring? That's right, we just learned about that. That is through nitration. Make it a nitro group. So the first thing you're going to do is put the nitro group on to make nitrobenzene, and nitrobenzene is a meta director. So then you put the bromine on, and it'll go meta, then H2 palladium on carbon, and you make your meta bromoaniline. But you have to put the nitro group on first, but before you reduce it, you can't reduce the nitro group to NH2 until you add the bromine, because nitro group gives us the meta director that we need. All right. How do you make this from benzene ring? How do you do that? Benzene ring, make this thing right here. All right. Now the thing is, this is actually in the book, so stop the video, work on it. But here's my question. All right, go through it, you can make it, but my question is then, when you finally make that product, how do you make this? Let's focus in on this molecule here. How do you go from this product right here to this molecule? Try working on that. Try retrosynthetic analysis. Start with this thing, start with this product, and see if you can work backwards to this. And by the way, you can't just find this, buy it, and do it. You're going to have to make this part right here. Any carbon that you add, anything can have no more than 6 carbons on it. Let's do that. Any reagent that you use can have no more than 6 carbons. And try to make this. See if you can figure that out. All right. So, good news. That ends the chapter, and that covers everything that will be on the first exam. So, study up.